day, friends. You're welcome to this session. It is session 1 of Unit 2. This session is looking at the mole, Avogadro's constant, and calculations involving the mole and the Avogadro's constant. This is yet another important aspect of chemistry. So let's proceed to look at the objectives for the session. Now, the objectives are to define the mole, find the Avogadro's constant, and finally solve simple problems on the mole concept involving the Avogadro's constant. So these are the things that you should be able to do by the end of this session. Before we start anything here, I want us to get this. You see, in our lives, we have used certain terms to represent certain numbers. If I say I want a pair of oranges, what do I mean? I mean I want 2 oranges. Now, if I say I want a dozen of oranges, what do I mean? I mean I want 12 oranges. So if I want to buy 24 oranges, I can just say, I'm buying 2 dozens of oranges. I don't want to say that's 24. Alright. So that will take care of huge numbers. We are using the terms to represent huge numbers. If we say somebody is celebrating a centenary, we know the number of years involved. So that saves us from huge numbers. Now, in science or in chemistry specifically, matter is made up of many tiny particles. And the particles can be atoms, they can be molecules, or they can be ions. For instance, when you take a cube of sugar, you can grind it. When you grind it, you can grind till you get the finest or the smallest particle of the sugar, which at that point you cannot even see with your naked eye, because at that point it becomes very small. So imagine when you just fetch a handful of sugar, the number of particles in that sugar, you will spend the whole of your lifetime counting, which you would never finish. If that is the case, then why don't we also use a certain term to represent a large number? So that instead of we mentioning that large number, we just mention the term and we know the number it represents. And so the mole is also used to represent a certain big or large number, just like in our lives we use certain terms to represent certain numbers. Good. Now, a mole of a substance, we are saying it represents a certain number. But how did that come about? How were they able to determine that let's use mole to represent this very number? Now, let's look at this. 12 grams, you see, carbon has isotopes. One of the isotopes of carbon is carbon 12. So, to serve as basis of comparison, carbon 12 was used. So, 12 grams of carbon was pegged at a certain number. Or, they said, okay, so let's assume that when we weigh 12 grams of carbon, these are the number of particles that it should contain. It wasn't actually counted because you cannot count. We'll come to that very number. So for that number that is contained in 12 grams of carbon 12, when we are able to count any particles of any substance such that we get that same number as contained in the 12 grams of carbon 12, then for that substance we have counted 1 mole, or we have 1 mole of that substance. If that's the case, then we can define a mole as the amount of substance which contains many particles as there are many particles, or as there are particles in 12 grams of carbon 12. Let's take it again. We can say that a mole of a substance, or a mole, is the amount of substance which contains the same number of particles as particles present in 12 grams of carbon 12. So that is the mole. Now, the mole has the unit mol. So the amount is the mole. Its unit is just mol. And usually it is represented by the symbol small n. So that is the mole. In the next slide, we'll look at that very number that is present in the 12 grams of carbon 12. So let's proceed. Okay, so we said that the number of particles present in 12 grams of carbon 12 was pegged at a certain number. What is that number? That number is what we are referring to as the Avogadro's constant or number. And so it was pegged at 6.022 times 10 to the power 23. So what it means is that anytime you say I have 1 mole of a sugar, it means you have 6.022 times 10 to the power 23 particles of the sugar. If I say I have 1 mole of oranges, then I have this big number of oranges. And this number, the Avogadro's constant was put on this number in honor of this Italian scientist Amedeo Avogadro. It isn't that he counted something or he did it. Actually, this is just a number that was assumed because you can spend the whole of your lifetime counting this huge number which you will not even be able to finish counting. So that number is called the Avogadro's constant or number. It has the symbol capital L or sometimes capital N subscript capital E. So Avogadro's constant, we can define it as the number of elementary entities in 1 mole of any substance, and it has the unit per mole. So it's usually particles per mole. So if the particles are molecules, then we can say molecules per mole or molecules in 1 mole. If they are ions, then we can say ions in 1 mole. If atoms, we can say atoms in 1 mole. So the next thing to look at is the relationship between Avogadro's constant and the number of moles. There is a relation. We have even already established that 1 mole contains Avogadro's number. Now, we have this relation capital N is equal to small n times capital L. The capital N represents the number of entities, being it atoms, ion, molecules, etc. And the small n represents the number of moles, whilst the capital L represents the Avogadro's constant or number. So that is the relation. And with this, we can now try an example where we need to do some calculations. An example is that we have been given 0.5 moles of oxygen gas, and we need to calculate the number of oxygen molecules and oxygen atoms. Okay, so let's proceed to look at our solution. We can put the relation, the formula we stated aside and solve it, or we can use the formula. So there are two ways of going about this. We are saying that 1 mole of a substance contains 6.022 times 10 to the power 23. So 1 mole of oxygen gas contains 6.022 times 10 to the power 23 molecules. So if 1 mole is equal to that number, then 0.5 mole will contain how many moles? So when we do this, we are going to just multiply the 0.5 by the 6.022 times 10 to the power 23 and divide by 1. That is going to give us a beautiful answer, which is 3.01 times 10 to the power 23 molecules of oxygen. Good. Remember, it is molecules per mole. So 0.5 mole times 6.022 times 10 to the power 23 molecules per mole. So the moles will cancel the per moles and we have molecules. Or we can just use the formula that we stated, capital N times small l, and then we do our substitution and we arrive at the same answer. The second, this is how we are going to go by. This time round, we are not looking at oxygen molecules, but we are looking at the atoms, oxygen atoms. If were to find oxygen ions, then we would express the molecule in terms of ions. In this case, we have to find atoms, so we have to express the molecules in terms of atoms. If we split the molecule, we are going to get 2 atoms there. And so, if 1 mole of oxygen gas contains 2 by 6.022 times 10 to the power 23 atoms of oxygen atoms, therefore, then 0.5 will contain 0.5 times 2 times Avogadro's number, and that will give us that beautiful answer. Or we can do our mole ratio to find the corresponding moles of the oxygen atoms. So in this equation, every 1 mole of the oxygen molecule or oxygen gas will give us 2 moles of the oxygen atom. If 1 is equal to 2, then 0.5 is equal to what? That is equal to 2 times the 0.5 divided by 1, and that will give us 1 mole. So if we have been able to do this to find the corresponding moles of the oxygen atoms, then we can use our formula. Capital N is equal to small n times capital L. We do our substitution and we have the same answer there. There is another example to find the number of ions present in 0.6 moles of calcium chloride. Remember, this calcium chloride that we have there is not ion. It's a neutral compound. But the question is asking us to find the ions. What it means is that we have to express this calcium chloride in terms of ions. We have to split it into the ions. And splitting into the ions, this compound was formed by a combination of calcium ion and then chloride ions. So we do, and then we balance. So Ca2 plus 2 ions of chlorine. Now, knowing this, then from this equation, 1 mole of calcium chloride is going to give us 3 moles of the ions. Remember, the question didn't ask us or didn't specify a particular ion. So we are putting the 2 ions together. So 1 mole of calcium ion plus 2 moles of the chloride ions. That will give us 3 moles. So if 1 mole of the calcium chloride is going to give us 3 moles or contains 3 moles of the ions, the calcium and the chloride ions, then that 0.6 moles of the calcium chloride will give us what? That's going to give us 0.6 times 3. So we are going to have 1.8 moles of the ion. So as we have done this and we now know the corresponding moles of the ions, we can go and then use our relation number of particles is equal to number of moles times the Avogadro's number. We do a substitution and then we have our answer right there. Another example is to calculate the number of atoms of hydrogen in 0.2 moles of ammonia. And with this, remember, we have to, this time round, we are not expressing in terms of ions, we have to express in terms of atoms. And we know that in ammonia, 1 atom of nitrogen combines with 3 atoms of hydrogen. So we have expressed this in terms of atoms. So we have to do a mole ratio to find the corresponding moles of the hydrogen. If it was the nitrogen, we would have found the corresponding moles of the nitrogen. So 1 mole of the ammonia gives 1 mole of the nitrogen and then 3 moles of the hydrogen. So if 1 is equal to 3 moles of hydrogen, then that 0.2 will give us what? It will give us 3 times the 0.2 moles of the hydrogen, and that will give us 0.6. If we know the moles, then we can go and then use our relation. Capital N is equal to small n times Avogadro's number. We do a substitution and we have our answer right there. So we are ending the session here, and you have these questions. Please try your hands on them, try solving them. Let's meet again in the next session.